Okay, in the last class we were talking about the simple pendulum with some friction, and we had proceeded to some extent, but there was a question asked at the end regarding the signs. So, let us just have you continued with it? Have you completed the problem? No, let's complete it today. So, we are considering a simple pendulum with a normal support. Your angle is theta. So, in terms of that, we had written the kinetic energy as half m. The linear velocity is L theta dot square. The potential energy is minus mg, sorry, mg is L cos theta. So, the Lagrangian is half m L square theta dot square plus mg L cos theta, right, and your Rayleigh function is half r L theta dot square is equal to half r L square theta dot square. In its term, when you write the p, that is the momentum, p was the derivative of the Lagrangian with respect to, in this case, theta dot. So, it will be this one, m L square theta dot. So, you notice that the momentum comes in terms of m L square theta dot, that is fine. So, this immediately gives, okay, since we were we wish to write things in terms of p and q, let us say theta is q. Okay. So, this is m L square q dot. So, your this immediately tells you q dot is p by m L square. So, this is the first differential equation. The second differential equation has to be obtained from the Lagrangian form, which that is where the confusion was. We have to write p dot is equal to. So, what was the equation that we used? It was derivative of the Lagrangian with respect to q I dot minus derivative of the Rayleigh with respect to So, in this case also we have to do the same thing. So, the first one would be yes, sorry, I will correct it so that the error does not carry through. Fine. So, when you evaluate this with respect to q I, which is this is q, so it will be, this term will yield its derivative with respect to q, this is q, will be minus mg L sin theta minus mg L sin theta, and the derivative of the Rayleigh term with respect to q I dot, which is r L square theta dot. So, minus r L square q dot, sorry, this will be q, because we are writing things in terms of q and p. So, mgl sin q minus r L square q dot, fine. In place of q dot, we have to substitute this in order to express the right hand side in terms of mgl sin q minus r L square, q dot is p by ml square, fine. So, we have got an expression with q dot and expression with p dot. We would now like to express that. Okay, so let me write it concretely so that things are clear to start with. We have q dot is equal to, we are expressing in terms of something times q, which is 0 in this case. So, I will write it here, plus 1 by m L square p, fine, this is 0, and p dot is equal to, here minus m g L sin q minus r by m p, fine. Okay, so this term is 0. So, you have two equations, two differential equations, and the next step, as I told you, is to locate the equilibrium point. In this case, what is the equilibrium point? You can easily see that if you substitute q dot and p dot equal to 0, a solution is p is equal to 0 immediately from this, and then if p is equal to 0, this will have infinitely many solutions at 0, pi, twice pi, minus twice pi, and all that, because it is sinusoidal. So, let us take one of them 0, 0. So, consider remember there will be another equilibrium point at pi 0, there will be another equilibrium point at minus pi 0, and all that. We will consider them, but first let us consider this. Okay, what is the next step? Next step is to locally linearize these equations. This is a non-linear equation because of the sign. We have to locally linearize around that equilibrium point, and for that we will have to take the Jacobian. So, the Jacobian is, so this is f1 of p and q, that is how we have written. This is f2 of p and q, right, that is why I wrote it this way. So, this is dou f1 dou, the first one is q, dou f2 sorry q and p, fine. So, what do you yield here? Dou f1 dou q is 0, dou f1 dou p is half m 1 by m square, dou f2 with respect to q you have fine, and this one is minus r by m. So, that is the Jacobian matrix. So, this is the Jacobian. Now, this Jacobian will have to be applied in the neighborhood of an equilibrium point, which is this. So, the moment you apply q is equal to 0, you have this term unity. So, this is only minus mgl. So, you have a overall set of differential equations, a overall vector field, and we are trying to locate what is happening, what is the vector field around this equilibrium point, and for that we have substituted, and in that neighborhood what is the equation? It will be, now we are writing it as x and y because these are the local coordinates, x dot y dot is equal to, what is it, 0, 1 by m L square minus mgl and minus r by m x y. Fine. Who was asking the question the last time about the signs? Yes, have you understood now? Okay, so these are this is the equation in the local neighborhood. Good. So what is the next step? To try to solve it, and for that we have to obtain the eigenvalues and eigenvectors. So obtain the eigenvalues of this. Do it yourself. Obtain the eigenvalues of this matrix. It will be minus lambda times lambda minus r by m plus m cancels off is cancels off g by sorry L.
Minus lambda inside the bracket, minus lambda inside.
This is minus, no?
Yes, sir.
Yep. So this is g by L. So that is equal to 0. I'll write it clearly. G by L is equal to 0. So what are the eigenvalues of this? Lambda is equal to, it will be minus r by 2, that will have to be, I'll put it here, plus minus root over, what is there in the root? R square by 4m square minus L. So these are the eigenvalues of the system. Let us see what do they imply. First, if there is no air friction, what does it tell? If there is no air friction, this term is 0, and the square root term is only minus g by L minus, and therefore it will be purely imaginary eigenvalues. If you have purely imaginary eigenvalues, what will be the behavior like in the state space? Circles. Circle behavior means, yes, oscillation. So it will be a normal oscillation of the undecaying oscillation of the pendulum. So a normal oscillation of the pendulum where the theta goes from the positive side to the negative side and theta dot also does so, that is represented as a circle in the state space. Clear? So for r is equal to 0, your state space representation will be right. No, I would not immediately say right, because I have put arrows. How do you know it is in this direction? Now that needs to be obtained from this equation really. How? You say that okay, I have taken a value of some value, positive value of x and no y, y is 0, which means x dot should be 0. 0 times x plus 0 times something times 0 is 0. So there is no component of x dot in this direction. What about the other one, y dot? Y dot is minus something times a positive quantity, which is a negative quantity, minus this times 0, which will be negative quantity, right. Negative quantity should be in this direction. So, this is right. Okay. So, these arrows are correct, but you should convince yourself that these arrows are correct, because they could have been opposite also. Clear? So, the moment I write something, do not immediately accept, first question, check, and then accept. Fine, that is one thing that is I am something happy about. What is the frequency of oscillation? Frequency of oscillation is where we express this as sigma plus minus j omega. This omega is the frequency, and omega in this case would be just g by l, root over g by l. So, frequency not only that, for this one and for this one the frequency would be the same. So, if you start from here, the time it takes to come back here is the same as if you start from here and you go around it and come back here. Frequency is the same for all of them. That is one of Galileo's classical observations, and that follows from this result. Okay. Secondly, if there is air friction, what will happen? Yes, if you consider air friction, this term will be there and this term is a negative term. So, it will be sigma plus j omega. The sigma is a negative term. So, e to the power sigma t times the sinusoidal term. So, that sinusoidal term will decay and it will be a spiraling inward orbit. Fine, that is fine. So, for r present, it will be right. Still there is a question of frequency, because starting from here it takes some time to come back here, starting from here it takes some time to come back here. So, what is the frequency now? Now, yes, now the frequency is changed, it is not the same thing, and it is changed by this quantity, and if r is small, this change is also reasonably small. Can you see that? So, the frequency will almost be the same, root over g by l, but change slightly by the extent of this. Okay. What is the damping factor? Damping factor is the sigma, which is this. So, depending on the value of r, it will decay. Clear? The other thing is that, important thing is that the frequency of oscillation does not depend on the amplitude of oscillation. Here also it is true. So, all these follow simply if you follow whatever we have taught from the first class to here, because we have taught you how to obtain the differential equation by the Lagrangian method, how to obtain the first order, how to obtain the Jacobian, how to solve the differential equations. That is what ultimately follows. Clear? Understood now? Fine. So, okay, just to give you some idea about the numbers, consider this equation. Just do this. You consider a very standard pendulum. What could be a nice weight of a bob? Say half a kilo. Okay, this will be half. Could be a nice length of a 1 meter. Okay. Okay. And what could be a nice value of r? 0.1. Okay. I am not trying to give you something for which you have to use the calculator. So, r is equal to 0.1. What is the unit? Newton seconds per meter. Is there anything else needed? G is 9.81. You will have to press the calculator. So, take it as 10. Okay, let G be 10. What is the unit? Okay. Now, do this calculation. Firstly, what are these? What would the equation be? X dot y dot would be equal to something times x y this is obviously 0 and second term is 2, third term is minus 5 and the fourth term is minus r by m minus 0.2. Nice figures. So, what will be the eigenvalues? Eigenvalues would be minus r by twice m, which is 0.1, minus 0.1 plus minus root over g by L is 10 and the other term is so 0.01 minus 10. Oh, you can easily see that this is negligible in comparison to the 10, so we will ignore it. So, this is approximately equal to minus 0.1 plus minus j root over 10, correct. So, if you have this as the eigenvalues, what is the solution of the system? You already know that. So, solution of the system x of t will be, in this case theta, will be C1 the first solution plus C2 the second solution. So, what will it be? You already know C1 e to the power minus 0.1 t times, yes, okay, let's write it as the vector x t, so that this is x and y. This will be something. What was that? Just open that page. Minus sine omega t, which is root over 10 t cos root over 10 t plus C2 e to the power minus 0.1 t. This is cos root over 10 t and sine root 10 t. That is solution. So, when you want to investigate about the theta, which is in this case x, first one, you will take the first line, and when you want to investigate the velocity, angular velocity theta dot, which is y, you will investigate the next line. This is capital X, yes. This is the vector x. So, you can see there is a sinusoid with frequency root over 10 and here is a damping term with magnitude minus 0.1, clear. So, this is how we normally solve, but that is true for only the equilibrium point, that is at 0 0. What happens at the other equilibrium point? Immediately the moment you try to do it, you will realize that it is different. Do that just once. Where was it? Here. This was the equation, this was the Jacobian matrix in which we had substituted 0 0. What is the other equilibrium point? Pi 0, pi 0. At q is equal to pi, you also get a period equal to 0. So, pi 0. If this is pi, what you have? Minus 1. So, this becomes positive. This becomes positive means, let us go back straight to the example that we are doing. What are the example values? Yeah, here. This value becomes plus. because then it will be easy for you to see. This fellow becomes plus, this fellow becomes plus means plus 10. What does it imply? No more complex eigenvalues, real eigenvalues. What else do you infer from here? There will be one eigenvalue which is 0.1 plus root over 10, another eigenvalue is 0.1 minus root over 10. Root over 10 is how much? 3 point something. Minus 0.1 is negligibly small in comparison to it. So, we can say one is plus 0 point something, other is minus 3 point something, and other is minus 3 point something. What is the character of that equilibrium point? It is saddle, because there is one eigenvalue which is positive and another eigenvalue which is negative. Clear? So, you can see the same system, as simple as a simple pendulum, harbors many equilibrium points of different characters. What would that mean? I will come to that later. But the point is that for every equilibrium point you have to calculate it, and you cannot assume that for another equilibrium point the same equations will hold. The local linearizations might be different. Fine. Okay, so we have understood what happens if there are real eigenvalues which are different, which are unequal eigenvalues. We have also understood what happens if they are complex conjugate eigenvalues and pure imaginary eigenvalues. In the first case, we have understood that it will be like this, right? Fine. Under which condition this will happen? This will happen when there are two eigenvectors and the decay rate along this direction is larger than the decay rate along this direction, which means e to the power something t, that eigenvalue, should be minus a larger quantity minus big, and this one will have minus small. Okay, the two eigenvalues. Is it possible to have okay, let me ask the question the other way. This will be this will be true when there are two eigenvalues negative, but they are different. What if they are equal? Forty-five degree angle. Why do you know it is? How do you know it is 45 degree? But he was raising a question. Yeah, normally if you have one eigenvalue, since you are first writing the eigenvalue and for that eigenvalue you are extracting the eigenvector, if you have one eigenvalue you will be able to extract one eigenvector, you will not get two eigenvectors. Okay. So, one eigenvector only. So, in that situation you will have one eigenvector only. So, eigenvalues real and equal. First point is that you will get for one eigenvalue you will one eigenvector. So, imagine that that is something like this. The other eigenvector you have not found. The whole idea of writing in terms of eigenvalues and eigenvector was that I wanted two independent solutions, and in terms of that I am composing a general solution. But here I have a problem, I have got only one. So, what is to be done in that case? What is to be done is, I am not going into the theorems and all that, one looks for another solution of this form. It will be, the first one will be x1 of t, this x1 of t is one solution is e to the power lambda t times the v, the eigenvector. That is true. When you compose, then C1 will come. When you compose and write down the general thing, then C1 will come. At this stage, C1 will not come. C1, this is one of the general solutions. The second one looks for of this form x 2 of t is equal to, it will be e to the power lambda t, all right, but another thing of the following form, that will be a 1 plus a 2 t and b 1 plus b 2 t. Okay. So, it is a time dependent term, but there is a proof that you will always get a solution of this form, which means the general solution x t will be then C 1 e to the power lambda t times v plus C 2 e to the power lambda t times this thing a 1 plus a 2 t and b 1 plus b 2 t. Okay. Let us do one problem, then this will be clearer. Let us take an example system where your x dot, this is example, x dot is equal to thrice x minus 4 y and y dot is equal to x minus y. Obtain the eigenvalues. The matrix is 3 minus 4 1 minus 1. So, it would be lambda plus 3 minus 4 1 minus lambda, and you have to obtain the 2. Check carefully. Yes, in this case the lambda will come out to be 1 for both. It will in both cases turn out to be the same. Have you done that? Convince yourself. What do you get? You get 3 minus lambda minus 4 1 minus 1 minus lambda, and then you obtain it. Got it? For this, what is the eigenvector? Well. You cannot say v is equal to 1 2. You can say there is, I have identified the direction, and any vector along that is the eigenvector. So, the moment you say 1 2, I will say okay, why not 2 4. So, yes, it could be, no, be careful. Well, I would tell me the eigenvalue equation.
X minus 2y is equal to 0.
The for this one eigenvector equation, is x minus twice y is equal to 0. Okay. Yes, in that case one solution, one possible eigenvector would be 2 1. Fine. If it is 2 1, then it is 0. Nice. Let us take it. So, one eigenvector good. So, the x 1 solution is e to the power 1 t e to the power t 2 1. That is no problem. That is trivial. Let us try to work out the next one. In that case, the solution is of this form. The solution is of this form. This solution must satisfy this equation. So, let us do this. We have, if you use this, then you have x dot is equal to e to the power lambda t, in this case 1, a1 plus a2 t, and y dot is equal to e to the power lambda t b1 plus b2 t. Fine. No, this is x, sorry, this is x and y. This gives x dot is equal to, this lambda is 1, so I can easily eliminate it. What is x dot? E to the power t, this will remain, because e to the power t will differentiate as e to the power t. So, it is a1 plus a2 t plus e to the power t a2 plus a2, fine, and this implies y dot is, do it, e to the power t b1 plus b2 t plus e2, right. Now, that should satisfy this equation. So, we would write e to the power t, you can see cancels off. Anyway, we will write x dot is e to the power t a1 plus a2 t plus a2, this is x dot, is equal to thrice x, which is 3 e to the power t a1 plus a2 t, right, minus 4y, minus 4 y is this e to the power t b1 plus b2 t, right. Similarly, okay, this gives what? This gives cancels off, and ultimately you get from here. Can you just simplify this? Can you just simplify this? It will be a1 here, thrice a1. So, bring it here, it is twice a1. Here it is a2 here. Okay, so minus a2. Then is there any term devoid of t? Yes, minus 4b, minus 4b1. So, this is the t independent term plus, what are the t dependent terms? Here is the a2, we have taken to this side, it is here thrice a2t minus a2t is twice a2. Then you have, yes, minus 4b2 t is equal to 0, fine. Similarly, form this equation, y dot is this. So, e to the power t b1 plus b2 t plus b2 is equal to, it should be, y dot is x minus y, x minus y. So, you have e to the power t a1 plus a2 t minus y is e to the power t b1 plus b2 t. This cancels off. Now, club together the t dependent and t independent terms. What do you have here? Then a1 minus twice b1 minus b2 plus, then the t dependent term a2 minus twice b2 t is equal to 0. Good. So, we have these two equations, and we intend to find out A1, A2, B1, B2 from there. Can you find? Try. See, the line of logic is that these two equations must hold independent of t, which means the individual the terms must be equal. So, this term will be 0, 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 has to be, else you do not get it 0 independent of t. So, write this equal to 0, this equal to 0, this equal to 0, this equal to 0, and then try to extract the result. So, we have equations like twice A1 minus A2 minus 4B1 is equal to 0, first equation. Second equation, I will write this one, A1 minus twice B1 minus B2 is equal to 0. Next two are the same, yes, that is the point, next two are the same, but that is not a problem, because you are trying to find out any A and B's which will satisfy this equation, that is it. So, now the next equation is A2 minus twice B2 is equal to 0. This equation I have written down, and this equation leads to the same thing. So, there is no point writing down. So, we have three equations. No, ultimately we have three equations. From these three equations, we are trying to identify how many are really determinable from here. How many are determinable? See, if I multiply 2 with this equation and subtract from here, this cancels off and this cancels off, you are left with A2 and B2, A2 and B2. Check. It gives the same equations. So, we need to assume 1. So, out of that A2 and B2 we need to assume 1. What if we assume it will be simplest, and then so let us assume B2 is equal to 1 and A2 is equal to, fine. Now, substitute here. Can you determine the other things now? No, you cannot do it. Yes, yes. So, out of which equation, if you substitute, you have A1, this you have substituted, B2 is substituted, A1 minus twice B1 is equal to 1. From here, you need to substitute something. So, what is the simplest? Let B1 equal to 0, A1 equal to 1, fine. If you put B1 0, let B1 equal to 0, then that gives A1 is equal to 1. See, after all, these four things satisfy the equations. So long as it satisfies, we are fine. So, we have assumed, so what? That is what we do whenever we are trying to identify a eigenvector. We assume one thing and then we get the other, same thing. So, we have obtained it, then we can write down the equation finally as the x2 t will be e to the power lambda t, which is e to the power 1 t, times a1 plus a2 t. A1 is 1 plus twice t, okay, and this is b1 plus b2 t, which is t. The total solution is x of t is c1 e to the power t. What was the first one? 2 1, no? 2 1 plus c2 e to the power t, 1 plus twice t and That is the solution. Clear? From here it is not easy to visualize a vector field. So, let us do that exercise. What will the vector field look like? The vector field will have one eigenvector, not two. Say this is the eigenvector, and your what is this term eigenvalue is plus 1, plus 1. So, if it is plus 1, then these are outgoing directions. Fine, it will go out along that direction, but there is no other one. So, how do we visualize? What will happen in the other places? What will happen in the other places is something like this. It will move in one direction like this, okay, and here like this. So, you can see around this all these things actually emerge along that direction, that eigen direction, but after that they change. Clear? How do we know this? How do you know this? There are two ways of knowing it. First, look at the equation. There is one term which is dependent on what we already know, but there is another term where the vector is dependent on time. Vector itself is dependent on time. So, it will be a time dependent thing. So, as it goes out, the vector will change like this. The other way of looking at it is that since you do not have another direction, try in whatever possible way of drawing it. This is the only way ultimately you will be able to draw, so that all the vectors emanate, go out in this direction. This is the only way you can do it. Try any other possible way. What is necessary? What is necessary is that if you give a slight perturbation from here along this direction, it will move along that direction. Slight perturbation any other way, it will first move along that, and then it will go out. The perturbation in the other direction will slowly build up. Fine. That slowly building up will take it away from here, but it should always, all the curves will be tangent to this line at the equilibrium point, and this is the only way you can draw it. Try drawing it your way, any possible way. You will ultimately see that this is the only way you can draw it. What, Shika, you have tried in something else?
So why not the mirror image about this?
Exactly, about the axis.
Mirror image?
This way.
About the eigenvalue line.
Oh, here. Yes, you could. Wait. That is exactly where I was expecting this question. There are two possible ways. There are two possible ways. That is, right, and the other. So, there are two possibilities, right. She has correctly pointed it out. Well, when we draw the circles, there were two possibilities, either it could go this way or it could go that way. How did we take the decision? On the basis of the direction of the vector at a very conveniently chosen point, mostly at some x value with y0 or some y value with x0. Here also there are two possibilities. Out of that, which is true, we will have to decide on the basis of the same consideration. So, how will you do? Take a point on the x axis y 0 and then substitute it in the original equation, which is where is it? Yeah, in that. So, what do you get as the direction of the vector? Both are increasing, right? If x and y both are increasing, then at this point it should be like this, which is possible only if this is true. Fine? Happy? That will be the vector field then. Clear? There are two possibilities, out of which we have chosen because of that consideration. Fine. Okay. Now, let us summarize what we have learned. In a system, you can have the eigenvalues. Eigenvalues will have we will have the positions. Supposing the eigenvalues are like this, what is the behavior like? In that case, the behavior is like this. This is the real axis, this imaginary axis. Stable. So, for this I will just make a box and draw. It will be, there will be eigen directions and the vectors will be incoming, right. Fine. For this, if the eigenvalues are here, it will be opposite of that. So, it will be fine. If the eigenvalues are, say, here, what will be the behavior like? You should be able to visualize. That is why I am telling. You should be able to visualize. Then the behavior will be inward, because the real part is negative. If it is here, spiral outward, nice, no problem. But suppose you have a system in which you are changing the some parameter and the eigenvalues move as this. Suppose you have the eigenvalues like this, and then as you change the parameter, they move towards each other, and at some point they collide, and then they move away from each other, or the opposite. Initially they were here, as you change the parameter they come closer and collide and they move out. Okay, consider that, it will be easier to visualize that starting from the real thing. So, it was like this, and then they move like this, at this point they collide and they move out like this. Can you visualize how the vector field will be changing? How? Draw these three situations, one after the other. Draw these three situations. One, first one, two eigenvectors, and then negative real part, negative real eigenvalues. So, you have like this. Okay. What is happening as you move closer? What is happening with the eigenvectors? This eigenvector will move and ultimately coincide with this. Okay. It does not just vanish. As you change the parameter, as the eigenvalues change, this will change, and at some point it will coincide with the other eigenvector. Then at that point it will become, suppose this fellow has moved and has coincided with this, only this remains, and it was like this. So, it will be can you see that it is almost on the verge of turning spiral? This is a critical situation where it is about to turn spiral, and then as it exits the real line, it becomes can you visualize how the vector field is changing smoothly? Okay, fine. That's end of it today. We will continue in the next class.